much. So, last week in the first and the second lectures, we have looked at proper actions in transformation groups. The definition itself is quite simple, but the property is much more involved, that it's not a local property, but a global property. And the first lectures talks about more topological properties, and then gave necessary sufficient conditions to detect the properness. And then the second lectures is connected with various local rigidity theorem and also its deformations beyond the classical Riemannian setting. And there we discuss more differential geometric features, and sometimes the proof utilize linearizations of the problem. And there we quantify properness in a stronger way. Namely, we formulate that stronger properness by some quantifications. And today, I talk about its relations to unity representations. And there, I also use another quantifications, but in the opposite directions. When the action is not proper, and then we try to quantify to which extent the actions is far from being proper. Okay. So let us recall some basic notions in unity representation theory. Suppose G is a locally compact group. We recall that a unity representation pi of the group Z is called tempered if it is weakly contained in the regular representations on Z. Namely, every matrix coefficients of the representations can be approximated uniformly on every compact set by a sequence of a finite sum of matrix coefficients of the regular representation on Z. Here, we don't assume pi is an irreducible representations, but we know from Mountain and Telemann that any unity representation with locally compact group can be disintegrated into irreducible representations. And such a decomposition is sometimes referred to as the branching law for restrictions and differential formula for inductions. For example, in the regular representations L2x, then what we can say is that this whole unity representations on L2x is tempered if and only if every irreducible representations appearing in the differential formula are tempered for almost everywhere with respect to the differential measures. So namely, that just one irreducible non-tempered representations showing up here would kill the temperedness of the these representations. So this is the feature of the definitions. And in the case of the Lie group, if the group is solvable, then all unity representations are tempered by a theorem of Planiski and Reiter. On the other hand, for semi-simple Lie group, tempered representations, there are several equivalence characterizations. So one is due to Cowling, Hagerup, and Howe, that they prove that unity representation is tempered if and only if it is almost L2. So here we recall that unity representations on a Hilbert space is called almost LP. Here P is greater than or equal to 1. If there is a dense subspace D in this Hilbert space such that the corresponding matrix coefficient belongs to LP plus epsilon for every epsilon. And in the case, if G is semi-simple, this P equal 2 case, namely almost L2 and temperedness is equivalent. But in general, this equivalence is not true. Okay. So as a warming up, we recall some representative theory of SL2R. By the classifications by Bergman, also by Hashanda, that irreducible unitary representations of SL2R consist of the following. So trivial representations and complementary series representations are non-tempered representations, whereas principal series representations, discrete series, and their limits are tempered representations. In this particular examples, Casimiro operator separates spherical irreducible unitary representations by its evaluations. And correspondingly, for example, if gamma is a congruent subgroup of SL2R, then Selbach's eigenvalues conjectures saying that all eigenvalues of the Laplacians on the mass waveforms is at least 1/4, and this can be reformulated by means of representation theory, namely the corresponding unitary representations is tempered. So again, we should note that just one irreducible non-tempered representations, if it appeared, then that would kill the conjectures. So later we shall see that usually sufficiency for proving the temperedness is more difficult than the proving the necessity of temperedness. And this is a feature. Okay. And for semi-simple Lie group, and also if pi is assumed to be irreducible, then there are extensive study of tempered representations for many years. Like as we mentioned, that there are many equivalent definitions of irreducible tempered representations if the group is semi-simple. And of course, this was used as a foundations for high-standard theory towards branching formula for the group manifolds. And roughly speaking, in the orbital philosophy, that such representations correspond to the regular semi-simple orbits, or in other words, it is induced representations from the relatively discrete representations, the Levy part of the Caspital parametric subalgebras. And more precisely, that Zuckerman gave precise classifications, which is a cornerstone of the Langlands classifications. And also, as we saw that Selbach's eigenvalues conjectures, Gann-Grassard conjecture is also built on such tempered representations. So this is some aspects of irreducible tempered representations. And now we consider in this third talk, we consider the following questions, namely, suppose that G and H are pair of Lie groups, and then we consider unitary representations of L2 Z mod H. If Z mod H has an invariant measure, we can just consider square integer functions, and if there's no G invariant measures, then we can just consider half-density bundle and L2 sections for half-density bundles. Then we have a canonical unitary representations on homogeneous basis. Then we want to find criterion to detect whether or not this canonical unitary representations is high-standard tempered representations. And if this L2 Z mod H is tempered, we call this homogeneous space a tempered homogeneous space. So this is questions about induction from H to Z, but also we may think restriction problem, namely branching problem. Namely, also we are interested to find a criterion for the pair of groups Z and H, such that the restrictions of unitary representations of G without G invariant vectors is tempered when we restrict to the subgroup H. And we shall see at the end of this talk that this second problem is related to the existence problem that we discussed in the first and second lectures for the co-compact discontinuous group gamma. Okay. So this is I plan to organize this third lectures in dividing into three parts. The first, we try to explain criterions for tempered homogeneous space. And then, building on these criterions, then we need some combinatory arguments for convex polyhedra that explain some classification theory. And then, so this A and B is for the inductions. And then thirdly, I discuss about the restrictions and then connections with problems for existence of compact discontinuous groups, namely questions from local to global problems. So homogeneous space is responsible for the local structures, and then discontinuous group is responsible for the global structures. And these questions we have discussed in quite different various methods in the first and second lectures. And then today also we discuss another method where we use unitary representations as a tool. So this is my plan for the third lectures. Okay, so we recall these questions that first we want to understand to find handy criterions to detect this canonical unitary representations is tempered. And in the case of the semi-simple Lie groups, we have seen that this corresponds to that this unitary representation is almost L2. And so we may consider refinement of these questions when G is semi-simple, namely find the best possible P that depends on this pair G and H, for which K finite matrix coefficients for these regular representations belongs to LP plus epsilon. And actually that the method that we introduce from now also answers these questions when H is reductive. But today I mostly explain the case when P equal 2. And when P is greater than P2, then this means that some singular unitary representations show up in the Plancher formula for Z mod H. And we know we can tell to which degree that this singular representation appears by some dynamical approach. Okay, and here I give a small remark that we are thinking about the questions if this L2X is weakly contained in L2Z. But so this is our questions. But also there are similar terminology, but different notions, namely so-called X-tempered representations. So for a wide class of homogeneous space, it is known that Plancher formula for L2X, we need only certain subset of irreducible unitary representations called X-tempered representations that those irreducible representations that are realized on function space on X with certain moderate growth at infinity. And this is a true statement, but it's an immediate consequence of functional analysis theory of nuclear space. But we are talking not this X-tempered representations, but we want to compare two geometry. So in this case, X homogeneous space and Z itself. Then this simple-looking questions actually triggers many new connections, interactions with other branches of mathematics, including topology, analysis, algebra, and combinatorics. And we explain some flavor of it from now. So first, in order to explain our criterions, first I explain some, introduce some functions. So given finite dimension representations, real representations of Lie algebras, then we define functions on the Lie algebra as follows. So first, take an element y in the Lie algebras. then Y acts on V as an endomorphism. And then in the complexified pictures, we may think with the eigenvalues. And then take real part of the eigenvalues and then further take its absolute value and sum up all of them. So this gives some functions on the Lie algebra H. This we denote by rho V, if V is a representation. And then obviously this function is invariant under the conjugations. And actually it is determinant by its restrictions to a maximal split abelian subspace of the Lie algebras. And if we restrict it to the maximal split abelian subalgebras, then the resulting functions is a piecewise linear functions. If this functions is adjoint representations, then our row functions is essentially the usual row functions, more precisely twice the usual row on the dominant Weyl chamber. We should note that our functions is piecewise linear, whereas the usual row function is linear. And if V is the arbitrary representations, then this is the new functions. Okay. So now let us look at the criterions, one of the main theorem. That our setting is the following. G is a real algebraic Lie group, and H is an algebraic subgroup. And G is not necessarily semi-simple, but if we consider the Levi decompositions, and then we may think of the maximal semi-simple subgroup. This is denoted by GS. And similarly, H is not necessarily reductive, and then we also may consider maximal semi-simple subgroup denoted by HS. And we may assume that HS is contained in GS without loss of generality. Okay. Then we have a natural representations of canonical representation of Z on the Hilbert space L2 Z mod H. So this is the unity representations. And we highlight its restrictions to semi-simple part. Then we have the necessary sufficient conditions. Namely, this canonical unity representations is tempered representations if and only if there is an inequality of two row functions, piecewise linear functions. So this is our criterions and proved jointly with Brunoa. Okay. And in the case G is reductive, that I will mostly focus on this case today. Then semi-simple part is just obtained by this commutator group. In this case, our criterions can be written in a simpler way. Namely, this canonical unity representations is tempered if and only if inequality between the usual row functions and the another row functions defined on the isotropic representations of the tangent space on the geometry. So this is a necessary and sufficient condition. And I explain part of the proof, and the proof is divided in 4 steps. And each step requires new ideas and different methods. And the first, instead of the homogeneous space, as a baby case, we consider linear actions, and then functions on vector space. And then in this case, that the main machinery is dynamical approach. And this is connected with what we saw proper actions. And actually, the failure of properness of the actions is quantified by using the volume estimate. So this is the main machinery that we shall see in quite detail. And then from steps 2, 3, and 4, we gradually start from the reductive case and then non-reductive case. And then the second step for reductive case, we use this dynamical approach, but also we need some global estimate of the geometry. So we need some results for global geometry. This is a method. And then today I'm not going to enter about a more general case for non-reductive case. Then we need complete different tools also we need. One is for some unit representations comparing two geometries without any morphisms. But we need to compare such a theorems. So this is more unit representation theory. And then another step is to consider sequence of Lie algebras, and then consider its limit. And then its limit may change completely the structures of the original Lie algebras. And then we chase correspondingly the geometry, and then also geometry changes, and then we compare such unit representations. So this the last two steps, I think I don't have a time to explain. But for the first two steps, I explain its idea, which is closely connected with the first lectures. So we recall that proper actions is defined for the continuous actions on the locally compact topological space. And roughly speaking, that we fix some small set in the geometry, say a compact set, then we translate by group elements. Then collections of the group elements that still has an intersection with H, which we denote by GS. And this GS is relatively small. So this is namely compact in this case. So this is a definition of the proper actions. So the definition is very simple, but we saw that this is quite delicate properties. And then in the second talk, we strengthen these conditions, this criterion. So we have explained some necessary and sufficient conditions to detect in the first lectures. Then in the second lectures, we strengthen these conditions and then utilize for deformation theory. And today, we consider opposite way that, so this is more proper, so strongly proper. So this is a failure of properness. But still, we can give some quantifications of properness. So two way of quantifications. This is the main idea of the proof. And symbolically, we may write this way, that this tubular neighborhood is a necessary and sufficient condition for properness. And then if the Cartan projections of the discrete group is away from this tubular neighborhood, this is a necessary and sufficient condition for properness. But if we are lucky that this distribution is even better conditions that outside of some cone conditions, then this angle is some quantity to say strongness of properness. And this notion is stable under the deformations of discontinuous group when the geometry is not necessarily Riemannian, so under certain mild conditions. So this is one way to generalize. But today we consider, so symbolically I use this figure that we think about the volume of this set. So to be more precise, let us consider that properness, as we saw that this set GS is compact. But we may also think about this volume, and so namely this S and GS. Then this is if we consider volume in X, then this is depends on group element Z. So namely volume is a function of Z. And if this set is compact, then this means that this volume is compactly supported continuous functions on Z. And then we look at these functions. Namely, if the action is not proper, then for some compact set S, this function is not compactly supported. But still, we expect that this function decays at infinities quite rapidly. And then to which degree the function decays at infinity would give quantifications of the actions, how the actions is far from being proper. So this is an idea of the idea for the connections with the tempered representations or LP representations. And so as a baby case, or more even simpler case, just consider abelian actions. So suppose R acts on R2, that we have seen several times of this figure last week. And then this actions is free actions if we remove the origins. And then, but this action is not proper. So every orbit is closed, but the action is not proper. So it's a quite delicate action. But today, I look at the asymptotic behavior volume. So suppose that S contains S is a compact set near the origin. And then, so this actions expands some directions and contractions to some directions. And then we claim that the volume estimate is given by the following way. To see that the simplest case is when it is a square, then TS is rectangular. Then only we look at the directions of the contractions, then we have an exact equality. So in general, we have such an estimate. So this is a very elementary considerations. And then more generally, we consider actions of reductive groups on vector space V. Namely, suppose we are given a representation tau on V. Then we have introduced functions rho V in red. This is a function on the algebras. But we also introduce just a number for each representations. So this number is denoted by PV. So this is defined as a ratio, a maximum of the ratio of the adjoint representations, rho H, so in green, and modulo over rho V, corresponding to these representations. Since these functions are piecewise linear, then the maximum is taken only on the unit sphere, and so this maximum exists. So this is a number associated to finite dimensional representations. Then we consider unitary representations of these groups on the space of L2 on this vector space, and then ask this volume. What is the best possible P such that this volume belongs to LP plus epsilon for any epsilon and any compact set S? The answer is that the best possible P is exactly this number PV. So we have already explained the proof. Namely, since this is a vector space, so the dynamics is very simple. That start from subset S. When S contains the origins, then so this case is a crucial case. If S contains origins, then we have a directions of the expansions and direction of the contractions, and then direction of the contractions corresponds to the negative eigenvalues of the transformations, and then the volume estimate is given by our functions rho V. On the other hand, for the Hall measures, we have an estimate if it is away from the wall by using the usual rho functions. Then comparisons gives the best possible constant P. So this is an idea. So it's a very simple and direct proof. Okay. So at this moment, I give one theorem as a baby case, namely temperance criterions when H acts on L2V, where V is a linear vector space. So since we have a volume estimate, and then by using equivalent characterizations of tempered representations by Cowling, Hagerup, and Roger Howe, that we conclude the following. Namely, the first one is temperedness. So we are asking whether or not this canonical representations on L2 space is tempered or not. And if this is tempered, then this number that we have just introduced is at most 2. So namely, we have an inequality of 2 row functions and vice versa. And coincidentally, also this conditions is equivalent to some another questions of temperedness, namely restriction problem. So we consider interrepresentation of SLV, which does not have fixed vectors, invariant vectors, and then restrict to H through tau. Then we may regard such a representation as a representation of H. Then this representation of H is tempered for any representation of SLV without invariant vectors. This is also equivalent. And the third conditions or more general we shall see at the last of the talk. But these 3 are equivalent. So this is a baby case of temperedness criterions, because the geometry is a vector space. But now let us consider more general case, but I explain when both G and H are reductive case. So in this case, as I mentioned, that the main tool is this idea of dynamical approach, but then this is not enough, and so then I try to clarify what is missing from vector space to homogeneous space. So, so we want to give a necessary sufficient condition for temperedness. And usually that, as I mentioned, that as we saw, for example, in the Selberg's eigenvalues conjectures, that necessary condition for temperedness is easier, but sufficient conditions is more difficult. And in our geometric approach, that necessary conditions correspond to some local estimate, and then sufficiency for the tempered representation correspond to the global estimate of the geometry that we shall see now. So if we want to use the same method for the baby case, namely vector space, we want to give a volume estimate where S is a compact subset of homogeneous space Z mod H. And we want to find a lower estimate and upper estimate of these functions as a function on Z. And the lower estimate will be responsible for the necessary conditions for temperedness. And then for the upper estimate will be responsible for the sufficient conditions. Okay. So let us consider starting from the lower estimate. So homogeneous space at the origins may be approximated by the Lie algebras, by exponential map, and on which the isotropy subgroup acts on adjoint representations. Then, by using the previous result of the vector space for here, we have a lower estimate for element Z, not in the whole group Z, but at least in H. So at least in H, we have an estimate. But then we have difficulties that we need to estimate not only the subgroup, but we need a whole estimate Z, lower bound. And for the upper bound, it's more involved because even for the action of H, so this is a local picture in the vector space. But in the global picture, this orbit may return to this S. Then volume is not necessary here, but also we have to add volume here. So upper estimate is more involved to estimate the contributions that comes back again. So we need some additional global estimate. And this can be done by using the idea what we have seen in the first lectures about properties criterions, like estimate of the simplest case is estimate of the eigenvalues. When we part out the matrix, then of course eigenvalues varies. And then we want to give a precise estimate of the error terms. And the simple way is to say that 1% of the eigenvalues of the 1% of the maximal eigenvalues is the error term. So this is a simpler way to estimate. But what we need is that does not depend on the maximal eigenvalues, but some uniform estimate of the error terms for non-compact set of matrices. And this is what we have seen in the first lectures in the criterion proper actions. And actually, we use such an estimate for this global estimate of the volume. Okay. So now let me explain the results. So for any, we want to understand what is the best possible P for which the volume belongs to LP plus epsilon for any compact set S and any epsilon. And this best possible P is given by means of this number corresponding to the actions of the isotropy actions on the tangent space of the geometry. So it's similar to the statement vector space, but the main difference is that in the vector space case that both are the same groups. But here, this estimate is a whole group G, but this number is defined only for the subgroups. So this means that the implication from 2 to 1 is easy, but from 1 to 2 is more involved because subgroups, information from the subgroups gives all information of the whole groups. So this is non-trivial part, and then I explained some ideas together with dynamical system, but also some uniform estimate away from the subgroups. So this is a dilemma. Then from this, if we consider P equal 2 case, we get the following criterions. Namely, the canonical representation of Z on L2 Z mod H is tempered if and only if this number is at most 1, or namely, row functions on the adjacent representations does not exceed the row functions on the isotropic representations. And this conditions is given by piecewise linear functions. So actually, this is a finitely many inequalities on the edges of the polyhedral cones. So it's to compute this, it is a question of some combinatorics of convex polyhedral cones. Okay, so let me give one example for this, how to compute such a computation, such inequalities. So we consider the following case. So suppose H is a triple product of SLPQR, and then this group is considered as a subgroup of SLP plus Q plus R in a standard way. But also, we may consider this is a subgroup of the much larger SL up to finitely covering, namely by using the quiver representations, where H, this triple product acts on this vector space as a quivers. And then this gives them embedding up to finite covers. Okay, then we shall discuss 3 unitary representations of these 3 groups. And then theorem is the following. So the following four conditions are equivalent. Namely, first conditions is that this triple product group H acts on this L2 functions on quivers is tempered. This is one condition. The second condition is that a restriction problem, that we consider this huge representations SLPQ plus QR plus RP, and then take any unit representation without invariant vectors, restrict to this subgroup triple product of SLP. And then this is tempered. This is another condition. And third one is we consider another group, namely standard embedding SLP plus Q plus R mod H. So this is not a symmetric space, and in general, this is not a spherical varieties. So multiplicity may be infinite, but we can still understand what is when this is tempered as a representations of these groups. So we are looking at 3 unit representations of different groups. And then the fourth condition is when this happens. And this happens when a kind of triangular inequality holds, namely this inequality. And the first and the two is theorem A1, baby case, and then theorem A2 is what we have explained for homogeneous space Z mod H. And let me briefly why the last conditions appears. So this is a combinatory computations, namely what we want to compute is such a conditions. And this, if we write down by the coordinate, this condition amounts to such inequalities. So this is an absolute values, and for all x, y, z satisfying trace-free conditions. So we want to compute when this happens, what is the condition on P and Q and R. So this is elementary but non-trivial to conclude that this is given by a kind of triangular inequality. This is a combinatoric convex polyhedral cones. Okay, so this is some aspect of our criterions. So as I promised that so this theorem can be generous for not necessarily reductive case, but more general algebraic groups. But now, by using this combinatorics, we can give some classification theory. This I want to explain now. Yes? So this one.
Yeah, I just asked about a general quiver representation if you eventually get same conditions.
So it of course depends on what kind of representations, and so not completely general quiver representations, but some quivers that appears. For example, in this quivers that comes from the upper half triangular block diagonal matrices, and if we have such some nice features, then we have we can compute quite precisely. But actually, that yes. So we have some classification theory for not necessarily quiver, but for more general representations. But for in the case H is a direct product group like here, then we need some assumptions to give a precise condition.
Okay, thank you.
Yeah, still there are a lot of interesting open questions, even for this quiver type representation. Okay, thank you. So so now let me discuss about classification theory. So of course it's not realistic to classify all tempered homogeneous space, or it's almost impossible to classify all reductive subgroups in reductive groups. But surprisingly, that it is realistic to classify all non-tempered homogeneous space, reductive homogeneous spaces. So this is fortunate and quite surprising, but it is realistic. And so I explain why. So I write very loosely that we can give a complete description of the pair G and H of real reductive algebraic groups for which L2 Z mod H is non-tempered. In other words, it's not realistic to classify all tempered homogeneous space Z mod H. But for non-tempered one, maybe it's good to look at examples. So let us look at such a homogeneous space. So this is in general not necessarily symmetric or not necessarily spherical or even not necessarily real spherical. But if it is tempered, non-tempered, then such a condition is given by one inequality and vice versa. And so the condition is not very complicated. And more precisely, we have the following features. Okay, so maybe first I explain how to give a list of all such lists. So first, we can give reductions to the case when G is simple. I don't have a direct proof for this, but already we have a criterions, and then by using some combinatorial argument, we can give a necessary and sufficient conditions by reducing to the simple case. And then second one is that comparing Z mod H and its complexifications on GC mod HC. And then we compare temperedness of different group, complexified groups and the original groups. And then again, I don't have a direct proof for this, but if we use some criterions, we have one implications, namely, if GC mod HC is tempered, then Z mod H is tempered. Then the main task will be to classify all non-tempered homogeneous space when GC is complex simple. Then the last step is that which real forms are still non-tempered or not. And the most difficult part is the third steps, and so I explain the third step. Then there's a nice features. Namely, if the homogeneous space GC mod HC is non-tempered, then roughly speaking, that HC has a huge factors. What this means? For example, if GC is SLNC, then HC must contain either SLPC, where P is more than half, or SPPC, exactly maximal subgroups. And for example, if GC is E7C, then HC must contain either D6 or E6. They are not maximal subgroups, but there are not many possibilities that contains such a subalgebras. And if this is E8, then HC must contain E7C. Then there are only 2-3 possibilities for such subalgebras. So this is by using our criterions and then some combinatory argument, one can give us such a list of huge factors. And also, we can state in a more general way that so this theorem is not only for complex case, but also real homogeneous space. So real homogeneous space is much more involved, but we can state in the following way. So we need some terminologies. Suppose that V is a representation of H. Then we define two subsets of the vector space V. One is that collections of the vectors for which the stabilizer is abelians. This we denote by VAB. And then another one is that the stabilizer is amenable. So this is a larger set in V. And we use these notations for the isotropic representations on the geometry. Then, by using tempered criterions, we have the following implications. Namely, if generic stabilizers on the isotropic representations is abelians, then canonical representations on L2 Z mod H is tempered unit representations. And if so, then generic stabilizers is amenable. And in particular, if the group is complex, then amenabilities and commutativity is the same. And then this means that it is a necessary and sufficient conditions for temperedness. Namely, generic stabilizers are abelian if and only if L2 Z mod HC is tempered. And the special case of this is already non-trivial that I'm going to explain. So we are looking at all reductive homogeneous spaces. And then inside, there are real spherical manifold, and then inside there are real form spherical manifold. And then more narrower one is symmetric space, and then even narrower one is complex reductive symmetric space. And what we claim is that we can give a precisely what is non-tempered ones, this set. And let me explain what is the connections. For example, in the case when this is GC mod HC is complex symmetric spaces, then combinatorial part corresponding to part of the Vaughan's minimal K-type theory, saying that if we have such conditions, then certain real form is quasi-split. So in his classification theory of Lagrange's so irreducible admissive representations. So this is this gives an alternative proof by assuming our criterions for dynamical approach, because we have seen that this conditions is tempered if and only if we have such an inequality. But in this inequality, if H is a symmetric pair, then this means that a certain real form is quasi-split. So this is some shortcut of the combinatorial part. In the case, the pair is complex symmetric pairs. So this part. So another one in connections is when Z mod H is real reductive symmetric spaces. So in this case, the Plancher type formula is proved by Oshima Sekiguchi and Delorme and van den Ban, like this form, that this is a kind of the Caspiter paradox inductions relatively to Z mod H. And this representation is relative discrete representation for intermediate semi-simple symmetric space. And then by using this Plancher formula, we would think that necessary sufficient condition for temperedness will be solved by looking at such a Plancher formula. But actually, not, because there are some delicate issues that discrete representations for reductive symmetric space is not like high-standard discrete representations, but some representations have singular parameters. And then also we need to cross walls several times. And then sometimes they vanish, and sometimes they don't vanish. And if they don't vanish, and then this might be a non-tempered representation. And if they vanish at some walls, then still it may be tempered. And so, as we saw that the sufficiency of temperedness is delicate because just one exceptional singular representation show up, then it kills all the temperedness. And so, by using the Plancher formulas, that one can prove one directions for here, but not other directions. And actually, there are some exceptional cases. This is a semi-simple symmetric space for which most of the spectrum are tempered, but there are some small part of the spectrum after wall crossing several times are not tempered, and then whole representation is not tempered. So this our classifications detect such a list of semi-simple symmetric space precisely. Okay, so this is some aspects. And also, we can also talk about a little bit about geometric quantizations. That L2Z mod H is considered as geometric quantizations of the cotangent bundle, as in the lecture of the GAM. Then we may expect that some in-orbit method may give an approximations of the answers. And because tempered representations is considered also geometric quantizations of some regular semi-simple quadrant orbits. And so if this momentum map image of the cotangent bundle of the Z mod H consists mostly from coming from this one, then that would be tempered. And one direction is always true, but in general, this equivalence is not true. But if the group is complex groups, H is not necessarily reductive, then one can prove that this is equivalent. Namely, if this momentum image contains density coming from this regular orbit, if and only if this is tempered. But for this equivalence, we need G is complex Lie group. Okay, so now at the last part that I like to briefly talk about, so this is an induced representations, but now I like to talk about a restriction problem. So let G be a Lie group, and then as usual that we consider G hat to be the unitary dual. And K is the maximal compact subgroup, then we write G hat K as a set of irreducible spherical unitary representations. Then this is a definition of Margulis that a closed subgroup H is called G-tempered subgroup if there exists certain L1 functions such that the matrix coefficients for K-fixed vectors is bounded by these functions uniformly. So we are talking about, for example, L2 plus epsilon for temperedness. So this terminology is, this is L1. So it's a little bit inconsistent for tempered homogeneous space and tempered subgroup. But this is what Margulis used this terminology. So I keep this terminology here. Then the main thing is that if H is a G-tempered subgroups, then this G mod H does not admit a co-compact discontinuous groups. So namely, this is an application of unitary representations to the geometry. Namely, there's no discrete subgroup gamma such that gamma acts properly discontinuously and co-compactly on G mod H. And so we have seen such several obstructions like Calabi-Marcus phenomena, or more generalizations, and also some characteristic classes obstructions, and also cohomological obstruction. This we have seen in the second lectures. But now we give another obstructions coming from unitary representation theory. And this obstruction sometimes overlaps, but sometimes disjoint conditions. And actually that we have seen previous lectures, such a case, space for constant curvatures and also SL3C or SL2C does not admit co-compact lattice. But the Margulis theorem does not apply to this one because H, the subgroup H are not tempered subgroups. But there are some other subgroups that Margulis theorem applies. So it's good to look at some examples which cases G-tempered subgroups and which are not. simple observation is that compact subgroups are always G-tempered. And if subgroup is G-tempered, then any subgroup is G-tempered. So this is obvious because we have such inequality. And then if this is true for H, then similarly for any subgroups. But on the other hand, maybe I finish in 2-3 minutes. Okay. So, for example, by using the estimate of the minimal decay of matrix coefficients of simple loops that are developed by Roger Howe and Jansri, Chuchenbo, and Hio, one can tell which cases are tempered or not. For example, if we consider standard embedding of SLM to SLN, then this is unfortunately not a tempered subgroups. But if we consider, for example, SL2R and irreducible representation of SLN, n-dimensional irreducible representations, then the image is either SL2 or PSL2. This is an SLNR tempered subgroups if and only if n is at least 4. So if this is a large n, then this is a tempered subgroups. And more generally, that one can give some classifications of tempered representations. And this is as a corollary of tempered homogeneous space. We needed to compute some numbers that we introduced PV. And this computation can also apply to classifications of such a tempered subgroups. So roughly speaking, that if we consider irreducible representations in a huge vector space, then the image is tempered subgroup of this huge SLV. So this is what example 5 says. And in such a case, we have proof. We have non-existence of co-compact lattice of this geometry. And the key idea, just a few words about the key idea, is that for proper actions, this is topological definitions that we have seen. But also, we may use compactness that volume is finite. And then, if we consider volume or functions, then we can use a functional analysis instead of the topology. Of course, the information is not very precise, but on the other hand, we have more method by using functional analysis. And then we relax the conditions for compact SNT, but this is singletons. And not every point, but just for almost everywhere. That fits better for functional analysis. And this is called measurably proper actions, which is much weaker than proper, but still some kind of proper actions. Then why the restriction from G to H appears? The answer is the following. We consider unit representations of Z on L2 G mod gamma, if gamma is discrete subgroups. Then we are looking at the unit representation Z, but restrict to H. And if the matrix quotient from Z to H is well behaved, then namely tempered cross subgroups, then we have that this action is measurably proper and H cannot be co-compact. And more precisely, the actual proof, we don't need the group Z and just use the volume estimate of these functions as we saw in the beginning of today's talk. And if volume, not the whole group Z, but when we restrict to the group H, has a good estimate from the above. So this is the difficult part for the upper estimate. Then we have measurably proper actions, but this is not compact. So this is this part is more dynamical approach of the proof. So I think this is a good point of stop. So thank you very much for your listening.